To wrap up this section, we're going to look at bounds for the remainder. When we are looking to find the sum of a series, we're looking at the limit of a partial sum. So a lot of times we're not actually finding the sum, but we're finding the sum of the nth partial sum, for instance. So there might be a difference between the actual sum of the series and then the sum of that nth partial sum. And we have a way to try to find the difference between those two values. We call it the remainder here with the integral test. So it says if the remainder r is defined as the difference between the sum of the series and the sum of the nth partial sum, it's going to be between these two values. It's going to be between the integral from n plus 1 to infinity of f of x dx and the integral from n to infinity f of x dx. And again, that's a way to try to find that difference. And many times it's going to be very, very, very small value. If instead of r sub n in the middle there, if you were to put s minus s sub n in the middle, and then add your nth partial sum to both sides, you would have equation 2 here. And this can be useful for finding the error in approximating the sum of a series. Capital S here is the actual sum of the series. The s sub n is the sum of the nth partial term. So we can use this to try to, again, find the error there. And we're going to do an example, and I'm going to show you how this works. It says, for the series, which is the sum of 1 over n cubed, it says use the inequalities in equation 2 with n equals 10 to find an interval containing the actual sum. And I'm going to stop there, and then we'll do the next two parts of this. So we're going to use equation 2 here to try to find an interval that contains the sum of this series. So I need a few bits of information. Since n is 10, I need to find the nth, or the 10th, partial sum. And to find the 10th partial sum, we'd have 1 over 1 cubed plus 1 over 2 cubed, all the way up to 1 over 10 cubed. And if you work this out to a whole bunch of decimal places, so technically this is not equals, it's an approximation, but I've got 1.197,531,986. So that's the first thing that I'm going to need. And then I'm going to need to look at these two integrals. So I'm going to start here with the integral that in this case, since n is 10, it's going to go from 11 to infinity. Of 1 over x cubed dx. So this is the limit as b goes to infinity of the integral from 11 to b. I'm going to rewrite this as x to the negative third dx. So we can integrate that very easily. So we have the limit as b goes to infinity of negative 2x to the negative second, or sorry, I said that wrong. We have x to the negative second over negative 2. Apologies there. And we're looking at that from 11 to b. Of course, that's the same thing as 1 over negative 2x squared. So substituting in, and let me come down here. We have 1 over negative 2b squared. Then it's going to be minus a negative, so plus 1 over 2 times 11 squared. Let me go ahead and fix that to approximately. As b goes to infinity, 1 over negative 2b squared is going to go to 0. So we're left with just 1 over 2 times 11 squared. And that's going to be approximately 0.0041322314. I've got lots of place values here. Now that actually takes care of the left side. For the right-hand side here, we're still going to use s sub 10, but this time we're going to look at the integral from 10 to infinity instead of 11 to infinity. And I am going to skip a couple steps because it works out much the same way. The only difference is that we have a 10 instead of an 11. So what's going to happen is it's going to end up being 1 over 2 times 10 squared, which is just 0.005. So now that we have all of that out of the way, we can find an interval containing the actual sum of the series. So using this equation 2, we can say that the sum of the series is between the 10th partial sum and the integral from 11 to infinity of 1 over x cubed dx. And then on the other side, we've got the nth partial sum plus the integral from 10 to infinity of 1 over x cubed dx. Thankfully, I have values for everything here, so we're going to add them up. And I am going to just take these out to 5 decimal places. So if you add the 10th partial sum to the value here of the integral from 11 to infinity, you're going to end up with 1.20166. And again, I am rounding that. So the sum is contained in this interval that at its lowest value is 1.20166. At its highest value, if I take the 10th partial sum plus this integral's value, you're going to end up with 1.20253. So the sum, the actual sum, is somewhere in that interval. So we now have found the interval containing the sum. So we've answered the first part here that they've asked us to do. But we're not quite done yet. It says, use the midpoint of the interval to approximate the sum of the series. So to approximate the sum, we're going to just look at the midpoint of the interval. So I'm going to add these two values together and divide by 2. So 1.20166 plus 1.20253 divided by 2 is going to give me the midpoint of that interval. And again, I'm going to round. So our sum is approximately 1.2021. And then finally, what is the maximum error for the approximation? Now, the length of the entire interval, if you were to subtract 1.20253 minus 1.20166, that would give you the length of the interval. And the length of the entire interval, if you subtract those, is going to be a little smaller than 0.001. So it's just slightly smaller than 1,000. It says, what is the maximum error for the approximation? Well, we looked at the midpoint of the interval, so our maximum error is going to be half of this amount. So our error is going to be less, again, than half of this. So our error is no more than 0.0001.